Okay, so in this talk, I'm going to describe Liquid Haskell and how you can use Liquid Haskell to turn Haskell into a theorem prover. But before I tell you how, let me tell you why one should use Haskell as a theorem prover. We should use Haskell as a theorem prover because software bugs are everywhere. As an example, in 2015, an airplane crashed due to a software bug. As another more famous example, we have Heartbleed, an OpenSSL cryptographic vulnerability that, due to buffer overflows, actually revealed sensitive user information into other users. So the goal of Sorry. Yeah, it's difficult to do it again. Yeah, sorry. Okay. Okay. So we use all these Lambda languages not to fix these bugs, but instead to make these bugs difficult to express. So towards this goal, we are using modern programming languages like F#, OCaml, Erlang, Scala, and Haskell that make heavy use of well-studied theories like strong types and lambda calculus, and make statements like that well-typed programs cannot go wrong. Now, to fact-check this claim, let's see if we can encode Heartbleed into the strongly typed language Haskell. So to do that, I'm going into Haskell's interpreter, GHEI, and I'm importing data text, a library that manipulates string, and I'm actually packing hat into a data text, and then I'm going to use takeWord16, a function that I import from an unsafe version of data text that takes as input a text, an index I, and returns back the I first characters of the input text T. So now, if I index pack with true, then the lambda wins, because Haskell says that you cannot use true, which is a Boolean value, as an index, because the index shouldn't be integer. But instead, if I use 500 to index the string hat, then I have exactly encoded Heartbleed, because what GHC will do is basically go into the memory at the place that hat in store and give to the user the 500 characters that live in the memory after hat. So it will reveal into the user information that the user is not supposed to see. So with this, we have encoded Heartbleed into Haskell. So the problem here is that the type of takeWord16 says that give me a text T, and then give me an index I, that is an integer, and I'm going to give you back the I first element of the text T. But the index can be every integer, from -infinitive to infinitive. So what we actually want is to split integers into the valid integers and the invalid integers. And the valid integers are only integers that are good indexes for the text T, that is integers that range from 0 to len of T. And with Haskell's type system, we cannot express this division of integers, but we can express it using refinement types. So we use refinement types to specify a type of take that says, give me as input a text T, and then as an integ, give me some integer v, so that this v is always less than or equal to the length of the input T. Now, with this refinement type specification for take, if we try to index pack with 500s, we are going to get back a refinement type error. And for this talk, I'm going to get back a refinement type error with Liquid Haskell. So Liquid Haskell is a refinement type checker that takes as input a code with some specification, and it returns OK only when the code provably satisfies the specification. And it does this by checking that all the function, all the arguments of the functions are valid with respect to the specifications of the functions provided by the user under whatever facts Liquid Haskell can get from the environment. So, in our example, we have the fact that the length of x is equal to 3 because we statically know that x is a string hat that has length exactly equal to 3. And under this fact, I want to check if the arguments to the function take are valid. So what I want to check is if my argument, that is a value that is exactly equal to 500, is a valid argument for the specification of take that says that the index of take should be less than or equal to the length x. So to check that, I have an implication. And the way I'm going to check an implication is via an SMT solver. So the SMT solvers are basically black boxes that take as input a logical formula, and they decide automatically if this formula is satisfiable or not. So in this case, when I give this formula as input to the SMT solver is going to say that this formula is invalid. So Liquid Haskell will create a refinement type error that says that the call to take is not provably correct. It doesn't provably satisfy the specifications for take. So this is Liquid Haskell. It checks using an SMT solver automatically if the arguments to the functions are valid. That means that the arguments to the functions satisfy the specifications that the user provided for the functions under fact that it can collect from the environment. And the question now is, what kind of facts can Liquid Haskell collect from the environment? So in the example that we saw, the fact that we used was that the length of hat is equal to exactly 3. But then we can have, in some programs, we can have other interesting facts. So for example, we may need to use that the append operator is associative. Or we may need to use that if I map reduce a function f on an input i's, this is exactly equivalent to just applying f to i's. And generally, interesting facts are theorems about Haskell functions. So to encode and prove theorems about Haskell functions, we are going to use Liquid Haskell as a theorem prover. So we can use Liquid Haskell as a theorem prover using 3 steps. So first, we can use refinement types to specify theorems about Haskell functions. The second step is that we are actually going to prove these theorems using Haskell. And the final step is that we are going to use Liquid Haskell to check if the proofs we provided for the theorems are actually correct. So next, I'm going to use Liquid Haskell as a theorem prover to prove associativity of list appending. So to begin with, I'm just defining a classic list type in Haskell. My list is either empty, or it is a cons of a value of type A and a list of A's. And then I am defining the classic append function that it takes 2 arguments, x's and y's. If the first argument is nil, then it just returns the second argument. If my first argument is a cons, then it returns cons of x and recursively calls itself. So with this definition of append, I want to define a type that actually describes that append is associative. So I start defining a type that says that for every input x's, y's, and z's of type L list, this type just returns unit. And this is my basic Haskell type that is going to prove associativity of the append operator, because then I can come and refine the result type unit to actually describe associativity of append operator. So my unit type, my unit result type, is refined with a property that says that if I append x's to y's and then I append it to z's, this is equal to append it x to the append of y's and z's, which exactly defines associativity of the append operator. So now I'm just going to remove the information that V is unique because I don't actually need it. And again, here I specify using refinement types associativity of the append operator. And the question here is, how can I actually define the body of the append operator? So the body of the append operator should be a unit Haskell value that actually proves that my left-hand side, the left-hand side of the equality is equal to the right-hand side of the equality. So for example, I could define the body of a sock to be just unit, but this will create me a type error. So Liquid Haskell is not persuaded by the unit that associativity of append holds. So what I'm going to do is basically I'm going to define the body of the sock so that I start from the left-hand side of my operation, and then I conclude that this is equal to the right-hand side of my operation under some steps that we will see shortly. And then I'm going to use this fancy infix operator that Liquid Haskell provides to basically cast whatever I have here into a unit so that the basic type system is OK. OK, so let's go and basically fill in the dots in here. OK. So I look at the type of my append function, and I want to be able to say that the left-hand side is equal to my right-hand side. And as my left-hand side is right now, I cannot do anything. But if I go only in the case that x is the empty list, it is easy to observe that n append to y's, according to the first line of my definition, is exactly equal to y's. So this function call is interesting because in the logic, this function call will basically insert the first line of the definition of the append function. So Liquid Haskell, after this call, knows that n appended to y's is exactly equal to y's. And then we need to go from the second line to the third. And then again, we observe that I know that nil appended to y's append this, according to the first definition, is equal to y's append to this. So then with this call to append and with the green calls to append, Liquid Haskell is actually able to prove that append is associative in case that x is actually the empty list. OK, so this is the proof of append associativity in case of the x list. And for the case, in the case that x is not nil, I'm going to show you how exactly things work. OK. No. You cannot see all the screen. What? Control 0? Command 0? I don't know. You cannot see whatever I have here. Yeah, the window is not good. View, enter full screen. OK, nice. OK, so this is a Haskell function I use as editor in my browser. OK, so I import prelude hiding the functions I am rewriting. And then I import a library proof combinators that comes with Liquid Haskell that defines operators like proof, defines QAD and the stars and the equality dot. So I am defining cons, append, as I defined it before. And I say reflect append into the logic, which basically means every time you actually apply append on concrete input, then insert these equalities into the logic. And I also tell Liquid Haskell to check that all my functions are total. And then I come and prove associativity. OK, so I have the nil case that it's exactly the one that I presented you. And now we have to fill in the dots for the cons case. So I start from the left-hand side. I want to conclude in the right-hand side. So what I say is, again, I go and rewrite. So I have cons append with cons. So I can just remove the cons out of my append and say that this is equal to cons x, x's append to y's. Then again, I have append with a cons, so I can again go and get cons out of my append. And now, what I managed to do is I have here the left-hand side of the theorem of associativity that I want to prove. And what I can do is that I can basically recursively apply the theorem to associativity and tell Liquid Haskell, oh, this holds because of associativity in x's, y's, and z's. And then if I just push cons inside my append, I have, I have the right-hand side. And Liquid Haskell comes and says, yes, this is a valid proof. So what is interesting about this proof is that Liquid Haskell checks that the information that you give me are enough to prove what I want. It also checks that the proof is terminating. So for example, if in my inductive, if in my recursive call, I just said, assume the proof, then it will actually go and create a termination error and say that, oh, I cannot prove this. And it also checks that my proof takes care of all the cases. So if, for example, I just here ignored the nil case, then Liquid Haskell will say, OK, your proof is not complete because you didn't take care of everything. And OK, so this is a proof of cons, of associativity of the append operator. And the only information that Liquid Haskell needs extra is I define a length on the list. And I say that, oh, to check termination of recursive functions on lists, just use the length information. And here I have another interesting example on how to use Liquid Haskell as a theorem prover that basically proves equality of map-reduce functions. So map-reduce is basically a function, higher-order function, that takes as input a function and an input list. It takes the input list, it cuts it into chunks. Then in parallel, it maps its chunk with a function. And then it uses an operator, intermediate operator, to reduce my result. So here I have a very basic implementation of map-reduce that basically says, take the input and chuck it into chunks of size n, then map my function f into its chunk, and then use an operator op to reduce its chunk, starting from the output of f into the empty list. So reduce is basically a fold operation that says that if my input list is empty, then just return my basic value. Otherwise, I apply the operator opt to the first element of the list and whatever comes next. Map is the classic Haskell map function. And chunk is just a function that takes a list and chunks into elements of size chunk. So then I have a recursively defined sum function that if my input list is empty, returns 0. Otherwise, it adds the first element to whatever sum comes for the tail. And I have the operator that combines the intermediate result is just my plus. And I define parallel sum to be a map-reduced sum where my intermediate operator is plus. OK, so the question that arises here is if I can prove that actually p sum is equal to sum. And I can prove it via refinement type that says that for every chunk size n and every list i's, sum of i's is equal to parallel sum of i's with a chunk size n. And to prove it, I need a higher order map-reduce theorem that says that I can prove equality of map-reduce on sum and plus if you prove me that sum satisfies right identity and distribution. So you need these two lemata to prove equality to prove equivalence of map-reduce. Distribution says that if you sum and concatenation of x's and y's, this is equal to adding sum of x's and sum of y's. And right identity says that if you add sum of x's to the sum of the empty list, this is equal to sum of x's. So we use the Liquid Haskell to prove these two intermediate lemata that I need. And then we applied these two lemata to a higher order map reduce theorem that says that for every chunk size n and every function that operates on lists and every fold operator op, if you prove me right identity, which means that op of f of x's and f of empty list is equal to f of x's, and you prove me also distribution of f, then for every input list, I can prove you back that if you map reduce f using the operator op, this is equal to just applying f to i's. So this is a higher order theorem for every map reduce function that satisfies right identity and distribution. And if you prove that, you get back equality of the map reduce operator. Exit full screen. OK. So I saw you a demo on how you can use Liquid Haskell as a theorem prover. And with this, yeah, I can conclude that you use Liquid Haskell as a theorem prover in 3 steps. First, you use refinement types to specify the theorems. Then you use Haskell to prove the theorems. And then Liquid Haskell machine checks that the proofs are actually valid proofs of your theorems. And with this, I want to thank you.
Okay, we have a little time for questions. I'm interested in the refinement types that you showed in the beginning, that they're able to put constraints on time. This looks a lot like the basic examples of a dependency type language. Can you say a bit about how they compare the refinement types and dependent types?
So the basic comparison is that refinement types are dependent types, but dependent types can be arbitrarily expressive. In refinement types, what we say that you restrict expressiveness in basically logics that are decidable, including uninterpreted functions, linear arithmetic, or whatever decidable logic the SMT knows about. So with this, you get less expressiveness, but you have the huge benefit of you ask all the queries to the SMT, and the SMT decides automatically, so the user doesn't need to write extra proofs. And then there is another difference, and the difference is that generally you put refinement types on top of an existing well-typed program, which means that refinement types only let you reject programs that the basic type system doesn't reject. While with dependent types, you aim more to increase expressiveness of your language rather than reject more programs.
I don't actually speak Haskell, so please correct me if I'm wrong, but this theorem prover mechanism, it looks like a full expressive way to proper device tests.
Because, I mean, testing is like you saw that the user has to provide proofs. So the user has to provide proofs when you talk about Haskell functions. When you need to unfold specific Haskell function, SMT doesn't know anything about the definitions of the function, so the user has to provide proofs. So for me, ideally, what you would do is like you would, I don't know, like maybe, like if you have a lot of time and energy, for me, it's better if you actually prove whatever properties you want. But if you want something that just runs and you don't have like the time or the tools to do it, you just test your properties to see if they're satisfied. Yes.
You just said that the system doesn't know anything about the definitions of the functions, but it seems like it does use the definition to check that your proof steps are correct, right?
Yes. So the system only, like when I reflect a function into the logic, so in my append proof, I say that reflect append into the logic, and this means that every time you use append on specific arguments, you go and unfold the definition of append exactly once.
Nice once.
Yes, exactly once. Because then, like, you could use the definition of append to the logic and say, do whatever you want for this. But the definition of append then would be something in the lines of, for every x's, y's, and g's, append of x's and y's is equal to, and it will be recursive. So the logic would need a decision procedure that says exactly how many times to unfold. And this decision procedure could go on and unfold forever. And there are some heuristic solutions that work for that, but like we don't want to rely on this kind of solutions. We want a type checker that is always terminating and is decidable and it is predictable. So we say just every time you use a reflected function, unfold it exactly once into the logic.
Okay, I think we should thank Niki again.
Thank you.